Good morning. We are picking up from where we ended in our last lecture, where we look at the interval in which the root is expected to lie. Here we want to find the root itself. We want to find the root of transcendental polynomial equations. So we will be considering four methods. The bisection or the interval halving method of false position or the chord method, the Newton-Raphson method, and lastly the secant method. So bisection method, so simple. Bisection method, that is iterative procedure we have here, the bisection method. We have mentioned up there how we found the interval in which the roots lie. So this is the interval. But the bisection method says that when you have that interval, that is the beginning one, that is the end. So starting from x0 to x1, or say a to b, that is the beginning interval or the initial interval. The bisection or the half method, that's what it does is it divides into two and check which of these does the root lie. Graphically, watch it graphically here. So we have this interval 1, 2. What we first do is divide that into two. So this is the first area. We divide into two. This is the first area. So we determine whether it is here or here, whether it's this side or this side, based on the mean value theorem. So definitely this side will be less than 0, then we say it's here. Then we have this also again and ask is here, whether it's here or is here. Mean value theorem will tell that this side is less than 0, is here. We have this is here, we have this. So we're going to have the interval continuously until the interval is approximately small. That is where the difference between these two intervals is less than the epsilon value. Then we say we have converged to the root of the equation. So that is what the bisection method does. The given interval is halved successively until a required approximation is obtained. So that's the graphical aspect. Mathematically, you can see it here. So the first thing we are saying that we say let's find some C, where this C is a plus b over 2. That is the halving we are talking about. A plus b over 2. That is the halving we are talking about. The next thing to determine is the stopping criterion. We find the difference between B and C. B and C. C is the new number and B is the number at the extreme end. It will change from one iteration to other, from iteration to iteration. If the difference is less than epsilon, then we stop the iteration. But if not, then we may have to continue to the fourth step, where we have to check the C, A and C. So I want to illustrate it with this. So my given interval, as I said, is A, B. Then I find C, which is A plus B on 2. So what I'm going to do here is to check the fourth iteration. Check it. The fourth iteration. That is what we have here. If we say the functional value of A and C, that is A and C, if it's less than 0, then we are saying that the root lies within this interval. It lies here. So we are setting the C, that's the median, as our new B. So this becomes a new interval AB. Otherwise, if it is greater than 0, which means the root lies here. And what happens then? Which means this C becomes our new A. And we're going to have the interval AB, and we start over. We will start the iteration all over again. We start the iteration all over again. So that is typically what we are talking about. We have the interval, we divide into 2. We name it C. We find B minus C. If it's less than epsilon, we have to stop the iteration. If not, we find the functional values of A and C. That's the first value and the midpoint. If we compute that and it's less than 0, then we say that this median or the midpoint is our new value at the extreme right. Otherwise, then the midpoint will be the value on the extreme left. Then return to step 2. Return to step 2. We stop the iteration when the difference between two successive approximations or two successive solutions is less than epsilon. This was explained in the previous lecture. This is a graphical illustration I've explained here. So this is AB, this is our C, so this becomes our new B. AB, this is our C, this becomes our new A. AB, this is our C, this becomes new B. AB, this is our C, it becomes our new A. Like that going. Advantage of the bisection method is that it is always guaranteed to converge. As I explained, if you are going to take and you know that your interval of approaching take is a doom and a drizzle, you know that definitely you get to take. Definitely you get to take. That's the interval. One coming from this side, one coming from this side. Definitely you get to take. But what we're saying again is that it's very slow. It takes time for you to obtain your solution, and it detects only a single root at a time. It detects only a single root at a time. So for functions which have 5 roots, you may have to repeat the iterations, or you may have to compute each of them separately. The first root, the second root, like that differently over time. So let's look at this particular example. When you find the root of the equation, x squared is equal to that, where epsilon is 0.05, we stop the iteration after the 5th, or we stop the procedure after the 5th iteration, when the difference between two successive approximations is not less than epsilon. If it's less than epsilon, we will stop. But if it's not less than epsilon, we are moving on to the 5th iteration. And we are also assuming that the root lies within the interval 0, 2. So straight to our solution. Iteration 1, we determine the interval first, and we said the interval is 0, 2. So A is 0 and B is 2. Then we find C, that is step 2. The median of that, so this plus that over 2, that is 1, that is C. Step 3 is to check the stopping criterion, B minus C. This is B, which is 2. This is C, which is 1. So we have 1. And this 1 is not less than epsilon. Epsilon is 0.05. 1 is not less than epsilon. Hence, we cannot stop the iteration here. We have to continue to the 4th step. So the 4th step is to check f of a times f of c to see whether it's less than 0. So this is f of a is 0, we put it into the given problem. This is the problem. So when 0 0, we are having it to be minus 3. Then f of c is 1, we substitute that here to obtain the functional value, and this is 1 plus 2 minus 3, that is 0. That is 0. So we move on. So f of a, this times that, that is what we are talking about. This times that, this times that. What do you see? F of a times f of is 0. This times that is 0. This times that is 0. Let me edit it so you can see it properly. So I've edited that so that you can easily see. I've edited that. So minus 3 times 0, which is 0, and this implies that it's less than or equal to 0. That is less than or equal to 0, and means the root lies between a and c. It lies between this interval. For simplicity, we say that we set the c as our new b, and hence the new interval is 0 and 1. Remember, a is 0, c is 1, a is 0. So this becomes a new interval for the next iteration. So for iteration 2, as you can see here, this is a and this is b. We go over again, we want to find c. This plus that over 2, that's 0.5. We check the stopping criteria, b minus c, that is this minus that, 0.5, and it's still not less than epsilon. So we move on to step 4. F of a, that is a0, that is that. F of c, that's 0.5, we are getting that. So we check whether this thing will be less than 0. So this times that, this is negative will definitely be greater than 0. So if it is greater than 0, what we do is we set c as new a. So c, our c value, where is c? This is c. So the c becomes our new a, and the interval becomes 0.5 and 1. 0.5 and 1, because this is our new a. So this is the new interval. We move on to iteration 3. Iteration 3. We have a and b again. We find c, and this is c. We check whether the difference between b and c, this and that, will be less than epsilon. Still not less than epsilon, hence we have to continue the process. We move on to step 4. F of a, that's 0.5, we get that. F of c, we get that. Then we multiply and see whether we are getting positive or negative. So negative will definitely be positive, and since when it's positive, then we are going to set c as our new a. So this is c, it becomes the new a, c becomes new a, and the interval becomes 0.75 and 1. 0.75 and 1. So we move on again. So that is the interval. We find c. Here we complete the interval and c, not still less than epsilon. Then we find f of a, f of b greater than 0. So still set c as our new a. So c becomes new a, and this is the interval. We move on again. Check that for c again. So this is what we are talking about, successive approximations. We are doing a sequence of approximations until a required interval is obtained. We have that is c, B minus C is still not less than epsilon. Still, we mentioned that this procedure is a bit slow, and you are seeing that we may have to repeat it over and over until obtain the required accuracy. Though B minus C is not less than epsilon, the otherwise statement in the question implies that the computation could be halted at the 5th iteration. So we will hold on the iterations here, and we will pick the last C value as the root of the equation. So hence we can say that the root of the equation that lies within this interval is 0.94. 0.94. We have mentioned earlier that numerical methods gives approximate solutions, not exact solutions. So this is an approximate solution or an approximate root that lies within this interval. That lies within this interval. That lies within. So the scheme, that bisection scheme, is only able to find one of the roots at a time. One of the roots. So this one did find the positive root that lies within the interval 0, 1. That lies within the interval 0, 1. A quick recap of the bisection method. As I said, the bisection method is one of the methods for solving transcendental or polynomial equation. It deals with halving the interval in which the root lies until a smaller or minute interval is obtained, and that interval will definitely be a point which is taken as the root of the equation. We took this, which will have two roots, but we are finding the root within this interval. We are saying we have two conditions to stop the iteration, either on the 5th iteration or when the difference between two approximations is less than this threshold. So we followed the procedure, step 1, step 2. We have iteration 2, iteration 3, iteration 4 until we got to the 5th iteration, where we use the otherwise statement to hold our process, and we realize that the approximate solution here is 0.94. 0.94. So this is an example for you to try. This is an example for you to try. We continue with the other methods for solving transcendental equation in the next lecture. Stay blessed and shalom.